Good morning, everybody. I'd like to thank first Jessica and Tim for the invitation, and I also like to acknowledge my co-authors, Frédéric Rollandon and Martin Vallée, students from Ecuador and Peru who have been involved in this work, and all the colleagues of the Joint International Laboratory that have participated to this work. So as we saw during the previous day, because of the relative motion of plate, the subduction interface need to accommodate it through sleep. Sleep can occur as rapidly as earthquake. They can occur as a seismic sleep at a steady state, and some pulse of accelerated seismic sleep during slow sleep event or after sleep. And during this talk, I will try to make an history of these different sleep modes at the central Ecuador subduction zone and to see how they are organized in space and time, and so that we can say something about the anatomy of the subduction interface. So the area that we will be looking at is the subduction zone of South America, where the oceanic Nazca plate is subducting beneath the South American continent at a velocity of 6 to 7 centimeters per year. And what we knew from previous studies, this shows a velocity field expressed in the stable South America reference frame. But we see that the convergence is partitioned, and we could estimate using area where we don't see any significant strain. We could estimate the motion of a North Andean sliver, which moves at about 1 centimeter per year with respect to South America, leaving about 4.5 centimeter as slip at the subduction interface. When we correct for the motion of the sliver, we can then get some interseismic locking map. And what we will be looking at is this area of high locking that we see in northern Ecuador. We also find that further in southern Ecuador and northern Ecuador, there is a 1,000 kilometer long segment which seems to accommodate the convergence through steady creep. So this area is interesting because it has experienced one of the largest seismic sequences during the 20th century. And all of the great and large earthquakes have been recorded by global seismometer and or tide gauge, enabling to have some estimate of their magnitudes. So this started in 1906 with the rupture of a several hundred kilometer long segment of the subduction zone. There are some debates about the size of this earthquake, and that will go into the uncertainties of the budget of the seismic moment. And what we know is that 36 years later, the same area seems to have broken again during a large 7.8 earthquakes in central Ecuador. 20 years later, another 7.7 earthquakes in northern Ecuador, and finally, in 1979, 8.2 earthquakes in southern Colombia. And this observation was the base of the asperity model, where you have discrete asperities at the subduction zone that may break individually during large earthquakes and sometimes infrequently simultaneously during great earthquakes. So I will first describe the work we did for the Pedernales Earthquake. That was a 7.8 earthquake with dramatic consequences. And one of the observations we have is that the peak ground acceleration exceeded 1G at some places, explaining part of the damages observed. So due to the network we had deployed during the year before the earthquake, we could observe all the motion, both the static and dynamic motion during the earthquakes in near field. And you see here the results from high rate GPS, where we see peak to peak 2 meters of displacement at some of the site. In terms of the static displacement that will constrain the sleep distribution, this is what we have from INSAR and GPS. And I would like to draw your attention to this motion. So we usually have a trenchward motion as you would expect for a subduction reverse event, but we have a southward component here. And this is what you would expect when you're above the edge of an elastic dislocation. So this constrains very well the southern extent of the rupture. So we did a kinematic inversion using high rate GPS and accelerometer. I won't go into the detail, but show you the result of our kinematic inversion if it works. Yes. So the red square is, whoa, my God. Yeah, the red square is the epicenter. We see little moment released during the first second. Then the rupture of a first asperities with 3 meter of motion, southward propagation, and the main moment release with an area experiences about more than 6 meters of slip over a 30 by 30 kilometers squared area. So we believe that this slip distribution is well defined, and what we want next is to put it into the context of the seismic sequence and the interseismic lockings that we had before the earthquake. So in terms of the comparison with the interseismic locking map, so we see that the earthquake appeared to have ruptured patches that were highly locked before the earthquake. So that's the good news for being able to anticipate the area of earthquakes from interseismic coupling maps. And we also see that some other patches seems to have be unbroken by the earthquake. I'll come to that later. And in terms of comparing the rupture area with the 42 earthquake, it looks like there are some uncertainties with the location, of course, of the slip for the 42 earthquake, but it looks like there is an overlap. So there are several observations that support this overlap, but I will show just one, which is the comparison of the seismic waveform recorded on a seismological historical station in the Netherlands when we can compare, correcting for the instrumental response, the two waveforms. So if they are aligned to the first P wave arrival, it looks like the 2016 waveform has a longer duration than the 42 earthquake. When we shift them by 15 seconds, you can see that we have a very similar waveform. So what we did is, since the source duration seems to be shorter for the 42 earthquake, maybe the rupture was bilateral. So we simulated an earthquake with an hypocenter located in the middle of the rupture we find for the 2016 earthquake. Use the rupture velocity that we have for the recent earthquake and use the slip distribution. And when we do this for this virtual earthquake, you can see that the two waveforms are very similar. So that shows, that's not a proof, but that's an indication that the similar waveform indicates similar mechanism and location for the two earthquakes. Because this is not a proof for doing the seismic moment budget, I will test two hypotheses. The first one is that there was large overlaps between the two earthquakes. So let's do some calculation. So we have 74 years between the two earthquakes. We have the slip rate, so we would expect a slip deficit of about 3.5 meters. And this is smaller than the 6 meters of peak seismic slip that we observed. That might be due to some dynamic of the rupture, so maybe a more reliable quantity is to integrate the slip over the rupture area. And when we do this, we still find that the total slip during the 2016 earthquake exceeds the slip deficit accumulated since 1942. And of course, if you do the same calculation for the 1906-1942 period, you also have that the 1942 earthquake was too big compared to the moment deficit accumulated. So let's see the alternative hypothesis that the two earthquakes were close but not overlapping. Then you need to integrate the moment deficit rate from the GPS, interseismic GPS over a broader area. And if you do this calculation, you still find that the two earthquakes released more a moment significantly larger than the one accumulated since 1906. we can do the similar calculation for the two other earthquakes, even assuming a 100% locking. For these two earthquakes, we still find that they had a magnitude too large. They released too much seismic moment compared to the moment to the current rate of moment deficit accumulation. So, an insight for another way to look at this is to look at the first result of marine paleoseismology. So this is a core here somewhere in northern Ecuador, where our colleagues found the turbidites induced by some of the previous, that they interpret as the consequence of previous earthquakes. So they could identify these turbidites for all the sequence during the 20th century. And what you see before is that there are very little events. There was a big event somewhere in the Middle Age, but it looks like there was a period of quiescence before having the sequence of large earthquakes during the 20th century. So that's basically the conclusion on how it works. We are not in an ideal earthquake budget where we would have the long-term plate motion, strain, and slip deficit, moment deficit accumulation that we will catch up during a single earthquake at a regular interval. We are more in a scheme where we accumulate stress during several centuries, and this stress is released through a sequence of large and grid earthquakes. And even if we have a grid earthquakes at the beginning of the sequence, there are still some remaining stored energy that needs to be released by a subsequent large earthquake. So this is basically something that has been mentioned before as super cycle, documented in some other subduction zones, and also for continental faults. Let's look now at what happened after the earthquake. So here is one of the time series. So you see before the earthquakes, the co-seismic slip, and then beginning of the post-seismic slip. What we see is that there were several large aftershocks, and some of the aftershocks have their own afterslip. So for the sake of simplicity, I will focus the study to the first 30 days after the earthquakes, to the early post-seismic phase. The second observation is that if we take any of the GPS sites located close to the rupture, we see that the afterslip starts immediately after the earthquake. If we look now at the GPS sites located 100 kilometers south of the rupture area, you see here in this time series that there is a delay of a few days before we have post-seismic motion or slip on the interface, and that will stabilize about 25 days. So we believe that what we observe here is a remotely triggered slow slip event triggered by the earthquake, by the main shock. So I will show a time-dependent slip inversion over the 30 days. We see during the first day that slip will start to develop at some specific area of the plate interface, up deep of the rupture. After day 3, we start to have the triggered slow slip event. We start also to have some afterslip developing down deep, and I will go on the animation. Okay, so now what we have here is the final cumulative slip after 30 days. Of course, there are some uncertainties and some issue of the resolution that we have on the slip on the interface, and these curves show different model allowed by the data. But I would like to mention here the red dots here are the cumulative number of aftershocks as a function of time for a given patch. Here, this northern patch. And you see that for all the patches that we have here, including the remotely triggered slow slip event, their number of cumulative aftershocks really look as the cumulative slip that we observe. So the interpretation is that afterslip is the main process driving the aftershock sequence in that case. we note two unusual characteristics of aftersleep. So the first one, if we compare it with what has been found for two other earthquakes in the South America subduction zone, for Pisco in Peru, Maule in Chile, we see that the aftersleep looks much larger during the first days and much faster. So that's one observation. The second one is that if we look at where we have aftersleep with respect to the interseismic coupling map, we see that some of the aftersleep occurred in low locked area. This is what you would expect from a simple velocity strengthening behavior for low locked area, but we also have large aftersleep that developed at patches, at asperities that were highly locked before the earthquake. So in order to go one step further to understand this peculiar behavior, we looked again at the interseismic phase and looked for slow slip events. So in Ecuador, we have regular slow slip events. We can find them using geodesy. There are also seismic swarms each time we see them in geodesy and repeating earthquakes. So I will use the three techniques to see how it's organized at the plate interface. So we will start with the northern patch where we have high aftersleep, and during November, during 2 months in late November 2013, this is what we observed. So we observe a slow slip event with triggered seismicity. The seismicity is organized into family of repeating earthquake, and we have a northern propagation of these slow slip events. So the total moment is about 6.3, and we see that the slip distribution for the slow slip event correlates very well with the area of large aftersleep. So we did the same search for the southern patch, and what happens is that we couldn't find any evidence from the geodetic observation. But what we have is that this area has regular seismic swarms that we observed since there are observations since '94. And the second thing that we did is to take some waveform from the aftershock and to go back, since we have broadband seismological record in the area. And what we see here is repeating earthquake activities that are sometimes activated and that witness some of the occurrence of some slow slip event that we could not detect it by geodesy. So finally, looking again at the GPS time series, we found another slow slip event. You can see here the time series, the transient in the time series. And when we model the surface displacement observed by GPS, we find some slip equivalent moment of 6.7 in these areas that also correlates, partially correlates with the area of deep early aftersleep. And of course, we also find some slow slip event in the area where we observed the remotely triggered slow slip event. So that's the cartoon summarizing our finding. So the first one is the information that we have during the interseismic period. So from the GPS velocities, assuming constant rate, so what we have is some heterogeneity in the interseismic locking. Okay, this shows high locking in red. What we have superimposed on this is regular seismic swarm synchronous to the activity of repeating earthquake. What happened during the earthquake is that only this area ruptured seismically. Okay. What we also observed is that immediately after the earthquake, as a response possibly to the stress increment, the large aftersleep developed mainly in area that had experienced a slow slip event before the earthquake during the interseismic period. So the consequence is that this area appears to have behaved consistently aseismically during the various phases of the earthquake cycle, regardless whether they appear to be locked or unlocked over a few years of GPS observation. Okay, so in a sense, we can understand the way it works. So we have stress accumulation in this area of the plate interface, but some of this area will slip from time to time aseismically through slow slip event. So there are two consequences. The first one is that they prefer to slip aseismically rather than seismically. And the second one is that they probably release the stress in the medium surrounding them aseismically and preventing then the seismic rupture to penetrate and to go into this area. So this observation provides a new way to look at the interseismic coupling maps. When we have red, it doesn't mean, at least in the case of Ecuador, that we will have an earthquake, that we will have a seismic rupture for this area. It means that we need to take the coupling map and to look and to document the different slow slip event and aseismic slip in this area. And some of them will release the stress they accumulate seismically. And I didn't mention that, but I should have put an S here because the two large aftershocks ruptured exactly this area. So that will be my conclusion. I hope that I could show you some spatial and temporal organization of the different slip modes at the Ecuador subduction zone. And there are some implications for the friction anatomy of the subduction in interface. What we see is that the simple view of having locked area that will have velocity weakening and that will rupture during earthquakes, as opposed to area with velocity strengthening that will respond in afterslip as a consequence of the stress increment generated by the earthquake. So this view seems to be much more complex in the case of Ecuador. And in particular, this is probably beyond my understanding, but we can imagine that velocity weakening may explain locking and the occurrence of the slow slip event, and this can also be, or velocity weakening patches may also experience after slip. And at least the fact that we see the slow slip event and the rapid early after slip at the same place suggests that they should obey to the same friction law. I don't know how this observation can be generalized to some of the subduction zones, but team last night showed very similar results for Costa Rica. But I believe that a better anticipation for the location of future large ruptures, and especially their ability to go up to the trench or not, can be gained by documenting precisely not only the steady part of the interseismic locking, but also episodic transient slip. Thank you.
We have time for some questions, and please use the microphone. I'll ask one question while anyone else is thinking. Can you say a little bit about the spatial resolution in your models and how well resolved overlap versus not overlap is in the models?
Yes. Well, this is an important question, of course. So a few elements to answer this question. So the first one is that in Ecuador, so you see the coastline is at most 80 kilometers away from the trench, and the average depth of the subduction is 10 degrees. So of course, we're losing resolution of slip close to the trench, and this is shown most probably in some of the slides when we explore the range of models allowed by the data. Maybe, oops, sorry. Yes. Yes, well, here you can see that there is really, you can even double the amount of slip, for instance, close to the trench for the southern patch. Nonetheless, for the relationship between the seismic rupture and the afterslip, this is well constrained, because you see most of the GPS data are located very close to the rupture here. And we did some resolution test, and this correlation between the afterslip and the slow slip event seems to be resolved, at least at the first order. So that means that in the case of Ecuador, in order to infer what I said, you need a resolution for patch of about 50 by 50 kilometers square. And this is reasonable, I would say, for station located maybe 60 kilometers away in average from the trench.
Okay, so I'm interested in that locked patch that seemed to have afterslip afterwards. So if you look in time, how long before the earthquake is it constrained to be locked? I mean, I guess the data start at some point in time, and I'm curious if you know, can you say that it was locked for at least 5 years, or at least 10, or at least 20 years before the earthquake? I'm curious about whether that might be an area that actually has long-term slow slip events, but rarely enough that we hadn't seen one yet by the time the earthquake occurred, or if it's something that actually really did appear to be locked for a very long period of time, but then experienced afterslip after the earthquake.
Yeah. So the continuous GPS network started in 2008. So the coupling map I'm showing is some kind of average corrected for the slow slip event that we have between 2008 and 2016. So we don't have this information, but the inference I would like to say is that with GPS we always have a small snapshot or short snapshot of the whole earthquake cycle. And what I would argue is that we can use this snapshot, look where transient slow slip event occurred, and remove that. We're still missing the budget over a longer period, but we still have this observation that part of the area we see as locked during a few years are able to release some of the stress seismically.
Right, yeah, I'm curious if the older campaign data are situated in the right place and good enough that you could say whether that pattern that you've seen from 2008 to 2016 either definitely held going back into the 1990s, or maybe it's maybe it's not clear. So, yeah, are the data good enough to actually test whether if we were to go back into the 1990s, we would have expected to see the same thing at that location? Yeah,
very good point. Okay, if we estimate velocities from campaign that date back to 94, and thanks for your effort at the time, so we see slight difference in the velocities, especially for sites at the coast. So we can attribute this difference to the regular slow slip event. At some point where we have a better temporal sampling, you can remove the trend that you estimate from the continuous GPS and look where in the campaign data where you have jumps, offsets. And then you can come back to the seismicity catalog and to see the seismic swarm, and they correlate. So there have been slow slip events before 2008, we knew that, and they significantly contribute to change the inter-seismic locking map I'm showing, yes.
Okay, we'll take one more question.
Is there time? I'll just ask one of my questions. The deep slow slip behavior is just as interesting as the shallow. And one question was, is the down dip slip consistent with what you would expect from stress-driven relief of the co-seismic stress change? And do you think there's anything unusual about this slow slip patch that also has slow slip events at 70, 80 kilometers, which is really, really deep?
Yeah. Well, I'm trying to think. This, if you look at the distribution of the aftersleep as we image it and compare it to the stress, Coulomb stress increment induced by the seismic sleep, you see that the correlation is not very good, either both for up deep aftersleep and the down deep aftersleep. It really looks to be 50 to 60 kilometers away from the main rupture. So what is strange in having found this slow sleep even before is that we don't see any coupling before. So we don't know if it's something due to our inversion. Maybe we should have extended our grid for the plate interface deeper. I don't know whether we could not resolve it, and we need to redo this. In terms of this deep aftersleep, of course, at this depth, we can't exclude viscoelastic contribution to the signal that we see. The only test that we didn't do any modeling, but what we did was to remove the GPS time series for sites located in the Andean Cordillera. And we run the aftersleep inversion and see how well we can predict both the horizontal and vertical component of GPS sites in the Cordillera. And we don't have any problem with that. And that suggests that aftersleep, even for the deep aftersleep, was the main process, at least explaining the surface deformation.